Mm.
Can you hear me now?
Yep.
I think I can hear you now as well.
Mm. Okay. Can you see the? Can everyone see the paper?
No.
No.
I can't see your.
I can see that MS Teams.
Ah, okay. How do I? Okay, share. Chrome tab, no. Window, no. Entire screen. Okay, I think that's the right option. And then now can you see the paper?
Yeah.
Okay, cool. So welcome everyone. Today I am going to be presenting Gradient Descent, the Ultimate Optimizer. And I chose this paper because it's one of the outstanding papers from NeurIPS last year. So it's fairly recent, and when I looked through it, it wasn't full of theory, so I thought it would be it sounds like an interesting topic, so I was like, I'll do this paper as the next paper club paper. It's actually based on a really simple idea, I think, which is I need to make. I'm just gonna have to bounce back and back and forth in case I have to let anyone in. No, I don't. Okay.
I can take care of that, Peter, while you present if you want.
Okay, thanks. So it's based on a, maybe we'll go over what problem it's trying to address, which is working with any gradient-based machine learning algorithm involves the tedious task of tuning the optimizer's hyperparameters, such as its step size, which is a tedious task. Besides being tedious, it's also time-consuming. So if we could find a way to not have to hyperparameter tune our models and just know that we had the right hyperparameters, I think that would be very useful because it would kind of remove a step in the model training process when you're trying to find the best model. Unfortunately, this approach doesn't extend to a lot of hyperparameters. Like, for example, choosing between different architectures is not something you could apply this method to. But the basic idea is to calculate gradients with respect to your hyperparameters. So you calculate your loss, and then you calculate gradients with respect to your hyperparameters. And so maybe let's talk about how this happens, how gradients are calculated in well, let's talk about first how we'll start really basic. So when you train a model using gradient descent of any kind, maybe stochastic, maybe over the entire data set, which is just called gradient descent, maybe atom, any of them, what you're doing is you have what you see in equation, in this unnumbered equation here. You have your weights of your model. F is your loss function. You calculate the gradients with respect to the weights of your model. And then you want to minimize your loss function. That's why there's a negative sign here. And you update it with some step size alpha. So you're just making a small step size in the direction that would decrease your loss at each time step. And so the way that these gradients are calculated is during the forward pass of the network, directed acyclic graph is created, which is also called a computation graph, or a computation graph is created, which is directed acyclic graph. And the way it looks is it has a single node without any predecessors, which is the loss function. And then all of its leaf nodes, so the nodes that have no successors, are the weights of your model. And each time you perform this calculation, you create this directed acyclic graph. And the point that they make here is that you could actually also make alpha a leaf node. And the question of how to do that is, well, the first question is can you differentiate with respect to alpha and your loss function. And there's a paper by this guy whose last name is Baden, which was written in 2018, where he actually showed how to calculate the gradient of alpha with respect to your loss function and your current weights. You have to keep track of your gradients with respect to your weights from the previous iteration in order to do it, but it's fairly straightforward. And so there's this author, what they did is they were able to calculate like a manual gradient, or do a manual computation to calculate the gradient and probably just hard code it. But one of the points that the authors make here is that, you know, there's a lot of different optimizers. They have other hyperparameters besides step size, like Atom, or like, I don't know, there's quite a few, but like momentum-based optimizers, essentially. And so first what they do is they take the hyperparameters of Atom, which is alpha, beta 1, beta 2, and this epsilon, and they calculate the gradient with respect to it. Although they have this letter M here, and I don't think they actually say anywhere what M is. Maybe I guess I don't think it's important to the point they're trying to make, but I was just thinking, like, I can't find M anywhere. But anyway, if anyone else knows where M is defined, let me know. They point out two things. One, calculating the analytical formula for the gradient every time for every different hyperparameter is tedious and error prone. And I actually think especially the error prone is a good point, because ideally there's a lot of things that are like very detail oriented, but not very complicated to do. I don't know, like solving a ton of algebraic equations, for example, which is probably how these gradients are derived, that are much better, like lend themselves to being done by a computer than they do by a human. So they're saying, why don't we just use automatic differentiation, so you never actually have to calculate the analytical formula for the gradient? And basically what they're saying is, you know, okay, we're going to use automatic differentiation, what they call AD, and we can actually just apply automatic differentiation to our the standard languages that have it built into their calculations. We can just apply it out of the box. There's like almost nothing we have to do. The key point that they make is that, or like the key realization of how you can do this really easily, is that is an important consideration at this point is for weights. So when they say at this point, they mean when you've updated the weights of your model and you want to update them again with another iteration, is for the weights to be detached from the computational graph before the next iteration of this algorithm. So before, and they say that is for the weights to be forcibly converted to leaves of the graph by removing any inbound edges. So we'll look at a diagram that describes this, just to make it clear. So the diagram that describes this is here. And basically, what they mean by detach is that when you update your weights, you disconnect the updated weights from the weights of the before the update, and in that way you don't have to maintain, like at each iteration you're calculating this computation graph for the gradients. You don't have to maintain like the previous computation graph. And they point out that over time the computation, if you didn't do this, over time the computation graph would grow taller linearly in the number of steps taken. And because backpropagation is linear in the size of the graph, the overall time would become quadratic time and untractable. Besides that, I just don't, I actually was, to me, this is like a trivial point, but I guess it does warrant saying. And I was actually thinking to myself, like, why would you even need to maintain the entire computation graph from when you started training. But anyway, I guess it's important more because what you can do is you can take this observation and realize that when you're updating your gradients, the alpha that you use actually has an impact on what your next. So when you're updating your weights, it has an impact on what the next weights are, which means that it has an impact on what the next loss is, and consequently, you can back propagate through to alpha in order to, and then update it to maximize or minimize your loss function. So you can see this is the standard stochastic gradient descent. You can actually just view it as gradient descent. The stochastic part is batching your data set. But so it has some hyperparameter alpha, and what you do is you detach the gradients, you detach your current weights, and you detach your alpha. So all three of these parameters are detached, which means that they aren't connected to the previous computation graph that you calculated during this iteration, and then you update your weights. So your weights become leaf nodes of the next graph. But the point that they make is that, okay, you can instead not detach your alpha, but because everything else is detached before, like the gradients of your weights and then your weight, the previous weights, that means that when you calculate your gradients for the next step, alpha will be viewed as a leaf node in the computation graph that you can update. And then here's how they update it. So at each next step, they have calculated the gradients with respect to alpha, and then they're just updating it with the same rule. So it's actually so simple, but very cool and an interesting point. And they have another insight besides the fact that you can actually calculate the gradients with respect to your hyperparameters, which is that this whole process can be done recursively. So, because one point that what you can see from here is that if you look at the this update of alpha, there is still a hyperparameter kappa that you have to choose, which isn't learned. But if you, I like this pseudocode, by the way. I think it really helps you understand the method. If instead, when you create like your optimization algorithm, like HyperSGD, instead of just passing in alpha or like the hyperparameter of the optimizer, you pass in the optimizer as well, then you can actually call this recursively. So you can stack hyperparameter or your hyperparameter calculation of gradients, like optimizing your hyperparameters on top of each other. So instead of having like just optimizing alpha, you optimize kappa, and if you want, you can optimize whatever the hyperparameter of kappa is, which means that you can create like arbitrarily deep recursions, and where you only have like the one hyperparameter at the top of it, or depending on what, if you're maybe one point that they make is that your optimizer doesn't necessarily have to be the same as the one that you're using. So for example, here in this equation, they're using stochastic gradient descent as their optimizer, but they could use Atom, then they would be introducing 4 hyperparameters as opposed to just one with stochastic gradient descent. And so yeah, that's the idea in the paper. And the benefit that they really highlight is that it makes training the models less sensitive to hyperparameter tuning. Is there anything are there any questions about the method? Or anything anyone wants to ask? I'm just going to go through and see what I highlighted. If there's anything I feel like I've missed. I don't think so. No. Nope.
I think
Yeah.
the cool thing about the paper is that it's like a simple but like really powerful idea, right? So it's nice to feel straightforward to understand, but then the effects are actually really cool.
Yeah, I agree. Cool. So we've gone over the method or the theory, well, maybe not the theory, but the method behind it. So let's talk about experiments. Another thing that I thought was really cool about the experiments was that they were done on like a single, not huge GPU, and they didn't take that long. So in terms of experimental design, I thought, because I always feel like when you're doing good experimental design, the question you should be asking is like, what's the least amount of work I can do to test my hypothesis? And I think that they did that here in terms of choosing some really simple experiments to demonstrate the value of this work. So let's go through the experiments. The first thing they do is they, you don't know how well this method will work with different optimizers, but also with different architectures. So the first one is they're seeing how their hyperoptimization, meaning their optimization of the hyperparameters of SGD, works on MNIST with a MLP or a neural network with one hidden layer and a batch size of 256. And then they said as a baseline, we use SGD is equal to 0.01. So if we look at the results, which are here, I think these are the most powerful results in the paper. This is their SGD with an alpha of 0.01, and they get a error of 9% with like a standard deviation of 0.05. And then you can see, so this is if you look over here, this is the results with stochastic gradient descent. That's where the kappa is also, where the learning rate of stochastic gradient descent is optimized with stochastic gradient descent. The error reduces to 3%, and then when they use the final learned hyperparameter, they get an error of 5%. One question I had here, I was thinking, is like, it seems that at different points in training, and for different at different points in the training time, and also probably depending on your weights, you want a different learning rate. So here they're fixing the learning rate and training the model. But I was thinking, I don't know how, I don't exactly understand why they're doing this. It's like, this is the converged learning rate of the method, but probably, I was thinking, why aren't we using like that doesn't make sense to me. I was thinking, since there probably is a different learning rate that's good at different times of training, this isn't a very powerful result, but I guess it's saying like, at least it converges to a better learning rate than the fixed one that you started with. Maybe that's the point. One thing that I think is really interesting is that if you look at the different learning rates that are converged to, they're actually very different between different hyper optimizers. Like when you use Atom, you get something that's like an order of magnitude larger versus Attograd, which is about the same. And then RMS prop, it's also an order of magnitude larger. But
Is this?
You can, yeah.
I had a question here because, yeah, I was also kind of looking at this for a while, trying to understand what it means really. Because, so if you take stochastic gradient descent, if I understand correctly, the learning rate doesn't change. If you just do standard stochastic gradient descent, you just fix the learning rate, and it doesn't get updated throughout the training, right? So then what this is doing is, if you're optimizing alpha while you're training, so you're effectively updating it as well. But for something like Atom, which updates the learning rate as it trains based on the momentum and I guess other stuff, but then it also updates it based on the loss function. That's where I get a bit confused. It's like it's doing a lot of things at the same time, and I struggle to hold that in my head. Like, what is it? what is it trying? What is it doing? I guess.
I see. So it's that with Atom, you're already kind of updating your step size based on how the model is, like model updates. So
Yeah, like what does it mean to converge to like a single learning rate? Like in the Atom cases, you know, the Atom, if you just look at the simple case, which is the Atom alpha, where they only learn the alpha, and it has 0.0021. Is that your optimal initialization of the alpha?
Yeah, I wish I could. I want to give you an answer, but I feel like even though I could give you a conceptual understanding of how Atom works, I don't know the specifics. So anything I say to you will be poorly informed. But I think it's a good question, and I wish I could answer it as well.
Yeah, no, I guess just an observation. Because Arvid, I think the red numbers are the like what alpha ultimately converges to.
Let's check that real quick, and we can. Oh, actually, I think it says it in the caption of the. So each hyperparameter experiment is repeated using the final hyperparameters typeset in pink learned by the algorithm. So whatever it converged to. One thing I wanted to ask everyone is, because I guess I have a problem with this, but this is I think this also has a lot to do with the fact of like the type of research I've done in the past. So when I was doing robotics research, if you said you had like a 2% improvement in performance or a 3% improvement in performance, even if you had these numbers, they'd be like, not that impressive. But I've heard that for a lot of benchmarks and NeurIPS, like getting even a 1% improvement in performance with these numbers. So I think a key element of these results is that the standard deviation is so low that you can obviously see that the change in performance is significant, even though it's like 5%. I mean, like, sorry, it's like by 3%, 3% points or 4% points. But it's like, all of these differences, like here with Atom, the difference in performance is like 1.5% between their baseline and then using their algorithm or the final resulting parameters. So I guess that it's statistically significant, but it's also just like, these are such small differences. It would be nice to maybe see it on a benchmark that has more widely varying performance based on maybe your optimizer parameters. I don't know. I was just thinking that these are small, but maybe I also think that's a bias based on the research I've done in the past. But yeah, you see such small differences between things. Another thing I was also thinking, and I don't know if I was thinking maybe they should have done a hyperparameter search using like some Bayesian method and had that as a baseline as well, besides just fixing the learning rate to some value. So if you had done a hyperparameter search for SGD on on MNIST with their model architecture, what results would they get so that you can compare it to that? I don't think they do that experiment or that comparison, because I always felt like the whole point is you don't want to have to do a hyperparameter search. So a useful thing would be to compare it to a hyperparameter search. Anyway, the results are, they say we find the hyper-optimized SGD outperforms the baseline by a significant margin. And statistically, yeah, you see that sometimes it's almost halved the error rate, even though the original error rate was low. They do the same comparison for Atom, Attograd, and RMS prop. And if we look at the results again, I'm not going to go through them because they're kind of the same. It's just like the difference in performance, like the starting performance is lower for all of them. So all of these optimizers already perform better than just standard SGD with the hyperparameters that they started with. but then also that means that the difference in performance is less. Here even, you can see that the performance is worse with the converged to hyper learning rate than the original one. But yeah, overall, it's better.
I wish
and
they
then-
did
Yeah.
I wish they did another level to compare.
Yeah. So then they've done it with an ML. They've done their experiment with an MLP, and they've done it on MNIST. So then they move on to CNNs, and they perform similar experiments on CFAR10. Here are the results. We'll just read. Again, they see better performance, but when they say better performance, they mean like it's less sensitive to the hyperparameters that you chose. So if you can see that here are the hyperparameters, like the step size or learning rate that they chose. And what is mu again? Mu is the momentum. Okay. And so if you look at these results, I guess they're showing that the performance doesn't vary as much when you do hyper-optimization.
But it actually, the training loss seems to be generally better, right?
With hyper-optimization.
Yeah.
Let's see. Only here, no. But yeah, most of the time it is better. And then I guess the optimal results, well, then I guess these are the optimal results on the training set. But the more important thing is probably test error. And there you have that the black line is the hyper optimized versions, and they usually outperform the non-hyper optimized. So yeah, we conclude that hyper optimizers are indeed beneficial for tuning both step size and momentum in this real world setting of a CNN. And then they also look at for the original paper on this, for I think ResNet 50, which is what they trained, they introduced also like a learning curriculum where they divide the learning rate by 10 after 100 epochs, or is it 100, and then another 10 after 150, and they're comparing their results to the results that they got for just learning the learning rate over time. And they say, first of all, they're pretty similar if you look at this chart here, but the final performance is also very similar, which you can see over here. And I found that more encouraging as a point as well, because I was like, oh, I don't like that there's all these different things you can do, or not that I don't like. It adds work to like search for the right learning curriculum as well when you're trying to train a model. So if we can get rid of a lot of the different kind of almost artistic choices that come with training models, or things that you need, like, or the search space of hyper parameters and methods for training models with something like this, that would be great. Then they, besides doing it on CNNs, they do it on language models, or like RNNs on language modeling. Again, they get, let's see, they get good results. So lower training loss or the same training loss, and then perplexity, lower is better, and it's like a way of measuring model performance for a language. Here they're the same, but at least for this relatively low learning rate, the test perplexity is better for the hyper optimized one. Okay, and then they've done MLP, CNNs, and RNNs, And then they talk about higher order hyper-optimization, and I just highlighted this because, and this is where they add like a level above. So instead of just optimizing your learning rate, you optimize the learning rate of your learning rate and the learning rate of your learning rate of your learning rate, and so on. And they say, so they found, in practice, we find that if the initial hyper step sizes are too large, the computation diverges for networks larger than the MNIST MLP. So we initialized each level's hyperparameters to be smaller than that of the previous level. So they're always like 2 orders of magnitude or something less than the original. And the result, which they have, is with a 3-level optimizer stack, a single hyper optimizer design obtains reasonable results in all of our benchmarks across several orders of magnitude of base level steps. So we can see the results here, where this is an indication of like the magnitude of the learning rate, and then test error, and then you can see for different heights, so how many the depth of recursion of the stack. And what I thought was cool is like for 2 and 3, you're always getting good test errors, even when you have like really bad learning rate choices. And the same is true pretty much across the board for like, this is for vision, and this is for RNNs. And let's see, what are these? Oh, then but one thing you might say to yourself is just, okay, you're adding a recursion into the training process, like how much additional time does it add? And they just do a calculation on training time. And on max, the stack height adds like 10% to the training time, but on average, it's like 1 or 2%. So yeah, overall, you could, like, if this, honestly, if this was like a more tested and tried part of PyTorch, I would just try this when I'm training models instead of doing a well, I would compare it to a hyperparameter search for what we do, but I would like it to be better so I don't have to worry about it. So basically what we've shown is in their experiments, it makes the model less sensitive to hyperparameter tuning, and in general does better. And then it doesn't add that much training time, and you can stack it, like you can have a recursion of the learning rate. And then they just talk a little bit about other related work. And then they talk about limitations in future work, which I actually think is important to mention, which is, they say one limitation of hyperoptimizers is that they cannot yet handle initial hyperparameters that are set far too high. So they can't deal with hyperparameters that are set really high. Makes sense, because then you have like an unstable training process. And that's just a problem. But I'll come back to this because I wanted to have a discussion about something that this all brings up. And it says our implementation also requires some care in avoiding certain bugs related to the computation graph management. And it says, for example, loggers must detach what is logged to avoid memory leaks because tensors are not garbage collected unless all children are detached. So I guess when they say children, they mean the learning rate is no longer a child. But yeah, this is a good point. I think a lot of, like in a lot of the code I write, we do detach metrics anyway, just as a failsafe. And then also for built-in LSTMs, we cannot be used because they silently modify the computation graph, which can lead to incorrect gradients with our system. That I think is a more major issue, because one of the nice things about PyTorch, at least, is that they have a dynamic. It's based on building a dynamic computation graph, which means it can change from iteration to iteration, and even between data points, and that's really useful, actually, I think, for doing research. So, and I'm wondering whether this means that would be hard to use this method with like just any model that you're trying to do research with. So anyway, as a conclusion, I like this sentence. It says, we described an elegant recursive implementation of hyperoptimizers in a reverse mode automatic differentiation system and evaluated on a variety of benchmarks. That's the paper. So actually, I'll wait to ask the question that I've been thinking and ask, does anyone else have anything they want to talk about the paper or any questions that they might have? Or comments? Okay.
Well, yeah, I had one kind of thought as we were going through the paper, which is like how have they released any code or examples, and if not, I guess like how I haven't worked with PyTorch or TensorFlow in so long. Like how difficult would it be to implement something like this on our side?
Let's see. So this is the code. It looks pretty.
Oh, cool. So they've implemented like the actual optimizers.
Yeah. So I think that it's out there. It's just so you have to worry about some of the limitations that they talked about. Like maybe the way your model is implemented means that you can't that you can't use this because of how it silently modifies the computation graph. But the fact that all this code is here is great. Classic research code with things like run on lines. Oh wait, let me go back to the paper. So they did release code. I think it would be pretty easy to just like out of the box use it. I was thinking like a cool quick experiment could be to use it. If I had more free time, I might try. I would try. Actually, I would like to try that out on one of our models. But there's a million things that would be nice to try out, so it's hard to prioritize. But since it's so simple, it's so easy. Maybe we could pass it on to the production team. Like Aquarius might find it as something to try instead of doing hyperparameter searches. The thing that I wanted to talk about was initialization of hyperparameters, and even initialization of the weights of the model that you're using has an impact on the final performance of your model. And I was wondering, and so we automatically have to use heuristics. Like even here, they had to introduce heuristics for the hyperparameters of the hyperparameters to set these values. And I was wondering if there was any way that we could make it a little bit more systematic without introducing a massively large, like a massive amount of compute. Because all of this suggests that, I mean, I guess, so what I was thinking about when I was thinking about this is it all depends on the smoothness of the loss landscape with respect to all of your parameters. Because if you have like an incredibly not smooth loss landscape, then there's nothing you can do. But if it's relatively smooth, you could do some kind of like random search, possibly even to find out good parameters without having to train the model. I don't know. What do you think about like research into initialization, just like this research allows you initialization of hyperparameters and weights? Yeah, well, I think that if there was some low-hanging fruit here, then something would have been done about it. So I doubt there is, and it's probably just like a problem where there's no structure to the problem that we can apply to make it easier. But maybe there is. It'll be interesting to see if in a couple of years this method becomes the default instead of hyperparameter tuning once they figure out some of the bugs in it. So we'll have to keep our eyes and ears tuned. Go on, stop sharing. Arvid, you just posted So you need extra code for each method rather than doing a per hand calculation. Yeah, just for each optimizer, because these are really just optimizing the parameters of the optimizer. It does calculates the gradients automatically using backprop, so you don't have to do the per hand calculation. Well, if there's not anything else, I think we'll end it here. And thanks everyone for coming. And just as I said before, we're going to be doing our next paper club is going to be in 2 weeks, not next week. And I hope to see you all there. And have a good weekend, everyone. Bye.
Thanks, Peter.